It is an incredible pleasure to be here today, and having been in the trenches with you back in the 70s doing water research, and we can add to the legacy that the president just said of Argentina, Macedonia, Egypt, throughout Africa, the work that graduate students and faculty here have made influence on here. Today, what I want to do is to try to kick things off, and I want to be broad but not comprehensive and sort of set things in a context for the rest of the day. There are some very important topics that are going to be discussed in detail at the panel. We want to put it into the bigger perspective. Because if you went last year to the water night, we have moved from night to summit, and which almost caused a problem because I thought the summit was at night, and I have to sneak out at 10 to go to a PhD exam. But what I want to do is put in context the incredible work that's going on here. And if you are working on a membrane in material science, so you can get a picture of how you're contributing to the global water issue. Or if you're doing something with thermodynamics to increase the efficiency of a power plant or renewable energy, what does it mean for global water? They all mean something, and that's what I want to try to do today as we put things together. So let's see. It has moved away from me, but that's okay. So what I'm not going to talk about is research that's going on at MIT. You know that. What I want to do, though, is give a little challenge of where different parts of the Institute may be able to address some of those issues. And I want this, since it's early, to be interactive. So when I start listing a few places on campus and programs that I think may be there, if I've left something out, just shout it out, please. I want you to be saying, yeah, I'm doing that, and I want to be part of that. Okay, so one of the things that's a problem is when we talk about water, okay? So the world's water, most of it's in the ocean. So what we need to have, what's in front of the water summit, which is implicit, is the freshwater summit. The oceans are really important. People from EAPS who are here will be screaming at us if we don't say that. And we'll see in a minute why it's so important. But the water of the oceans help to decide or influence what the water is on the land. But then if we look at this, so we have this, only 2.5% of the world's water is fresh, and as we bring it down, we find most of that's in glaciers or groundwater. That's unacceptable. And then we look at that's available, most of it's in permafrost, and then we have some in lakes and the rivers and swamps. So it's a very small part of the total global cycle, which is this fresh water, which the human and aquatic ecosystem are working on. Now, when we talk about a water summit, it's pretty clear we're at the right place, right? What is the MIT mascot but a beaver? And what do? They cause havoc to humans. They build dams. That's why they're engineers. And they build these dams for their home, but they also prohibit the movement of water, but it makes little ecosystems. So I think it's an appropriate thing that MIT is a place that's focused on water and will continue to be. Now, this is the other important thing as we look at the global water balance. So we've moved from the global water, and we're now looking now at the freshwater balance. And what we see if we look over on the right for the oceans is it's 71% of the land area, or of the surface of the Earth. And then there's some people in EAPS that make these computer models called aqua planets, where there's no land. That bothers me a little. But what we see on the ocean is that there is more evaporation than precipitation. So there's a problem. Why aren't they drying up? Well, what happens is this evaporation gets spread out through general circulation, and it comes over the Earth, and it precipitates over the Earth. And over the Earth, we have a net precipitation. So the precipitation is greater than the evaporation, and then we have surface and groundwater outflow, which keeps the mass balance here. So the whole issue is you can see how important this is, that this is what the climate modelers and meteorological modelers do in their general circulation models. They are modeling this system globally, the mass and energy of that. And that's why when we look at climate change and greenhouse gas warming, it will disrupt this system and change it somewhat and its spatial patterns. So we see that there's about and the units here are cubic kilometers. Okay, kilometer by kilometer by kilometer, a cubic kilometer of water. Now, where is that freshwater cubic kilometer? Okay, the total runoff we saw is about 38 cubic kilometers of water. Spatially inaccessible, it is about 7 of that. No humans are there, it's remote, and in the Amazon and other places we wouldn't get it. So we end up with about 31 available. But then temporally inaccessible is floods. When we have massive floods coming down the Ganga, the Congo, the Amazon, the Missouri, the Mississippi, they aren't available all the time. So we end up with readily available water supply of about 11 of that 38 that's there for us to easily get a hold of. If we have built some reservoirs with dams and other things like our beavers, and with that we can capture 1.5 of that 20. So we have, for water supply for human use on an annual basis, about 12.5 cubic kilometers. We as humans withdraw about 5.5 of that, and in different parts of the world, different percentages of that are put back, but generally we're putting back about 60% of that. So we're only consuming, by putting it back into the atmosphere through other means, in terms of on the water, about 5.5. So where's the global water crisis? We can go home. We're using 15% of the total and 45% of the available. This should be enough, right? Well, the problem is that's a global picture. If we look at the runoff, what you see is this problem. This is a scale of where the runoff is in the globe. And you can see just the United States, for example, and why in any of the work that we're doing, say in our joint program, where we're looking at large-scale economic models, if you try to do something, say something about water in the United States as a whole, you miss it, because we have lots of water east of the Mississippi, not very much west of the Mississippi. If you add that up, per capita, there's a lot of water, you can go home. But it's regional problems. So we see that in the US, we see it in Africa, we see it in all of the continents, pockets of aridity, and then also pockets of flooding. And so this issue here of spatial disaggregation ends up, as we look at it on the continent scale, and we just sort of point out in Africa, they have 10% of the world's water, but 12% of the people. Even more dramatic in Asia, they have 35% of the world's water, but 65% of the people. And here in North America, we have 15% of the water and 8% of the people. So we're rich in that. So the issue is now coming, there's enough water, but is it where we want it, when, and how do we deal with that? So what it means is, and this is some work from the International Water Management Institute, is we end up with hotspots. And so the bright red are hotspots of places that are extremely physically water scarce. And we're going to be learning a little bit more in the talk after me, as we start talking about institutions and economics, what they like to call economic water scarcity, where there isn't the resources to provide the water to the people due to poverty and other economic issues that are going on. So you see we have this hotspot. We can zoom in even more if we want on different pixel resolutions. Now that we have GIS, we can do anything. But you can kind of get the picture that we're focusing on certain hotspots. The other thing that becomes important is the variability in time. So we have a problem in space. The water's not maybe where we want it to be, where the people are. But then we don't have this constant 38 cubic kilometers of water and 12% of it in the US the same every year. We have this stochastic process, this varying time, which means droughts and floods. And so that's the life of a civil engineer, is protecting society from droughts and floods and keeps us in business. So you can see the wide variability of that, and it changes. And as we look at this global scale and this global picture of where is the water, one of the things that we can be doing here at MIT is Earth and Atmospheric and Planetary Sciences. It's really important that we start understanding this global system and how changes to the environment, global changes, not just greenhouse gases, but land use changes, and emissions of pollutants and different, how that might change this spatial variability and even the temporal variability. One of the big concerns is As we increase the hydrologic cycle with warming, will we have more droughts and more floods? Doing research on that. So there's a lot of work we can do on that. The other thing is, these are greatly unknown numbers. If we put the error bars on these numbers, so there's a lot that can go on and a lot we can learn from both aerospace and astronomics and all the space satellite work and remote sensing in general. If we can do a better job in remote sensing, we're going to be able to get more precise on this and help us do better planning. The other thing is computationally. As we get these big data. It's a huge issue. How do we process this data? What does it mean? How do we get that at the resolution we want? So all those departments that are out there doing those things can really contribute to the water issue. And then, so we have this issue of time and space. Where is the water? Then we want to look at water use. And the issue is not all water use is the same. And some water use, what we like to do is withdraw it, dirty it, and put it back. Or in the case of thermoelectric cooling, we want to take it in, heat it up, and put it back. So there is some consumption, and we won't get into the details, but basically we're altering the water and affecting the aquatic environment by that. Other places where we use it, for example, a center pit irrigation scheme, there we're putting it on and the plant is consuming it. We have a closed water system, so that water is going to be evapotranspired into the atmosphere and go somewhere else and fall again. But out of that river system, it's gone. And that will consume anywhere from 60 to 70% of the water, depending on the efficiency of your system. And then we see all the other different types of water use for aquatic wildlife, for recreation, for just nature, using it there, and we'll store water to put it in our products, as in beverages, and then to supply it to our human needs. So all of this is different. And so as we look at this, what the use of the water affects the issues directing this timing issue and its spatial issue and how we address it. So in terms of freshwater use for the globe, 70% of the withdrawals are for irrigation, about 10% for domestic use, and 20% for industry. And industry, primarily that is electric cooling. And we'll look a little bit more at that. So this energy-water nexus is really crucial as we look at that. Of that irrigation water, 60 to 70% of that is consumed. Of domestic and industry, very little of that's consumed. On the 15 to 10%, we use it, dirty it, and put it back. So that's one of the issues. If we look at the United States, what surprises many is that the predominant water withdrawals in the United States in 2005 were for thermoelectric cooling. And of that withdrawal, 80% of it is on the eastern side of the Mississippi River, and 20% of that is on the western side. And that's not just because that's where all the generation is. On the western side, they use recycling with cooling towers and cooling ponds, where you take in much less water and you cool the water through evaporation, so you consume a lot. Here, we take it in, heat up the water a little bit, and let it go down the stream and have conduction of the heat to the atmosphere. We see our next largest is irrigation. But if you look at that, there's two parts of the US, the eastern and the west. The eastern's dominated by thermoelectric cooling, the western by irrigation. And then we have our public supply and our industrial supply. So the actual amount that goes into manufacturing is very small. And if you put values on this, as Professor Fisher is going to look at later, it changes the picture, because one of the things driving us in the western US is the prior appropriations doctrine that says first in right, first in time. So if a farmer takes this water and is putting on hay to feed horses in Colorado at a value of $20 per acre foot, and the city of Thornton wants to pay $10,000 an acre foot for domestic, nobody can make that person do it. And some places there's not even the water allowed to make transfers temporarily, or the water markets to do that. So we'll see that as later. The nature of your water is real important. Now, it's not just in the US. In Europe, again, Europe is like the US, we have different hydroclimatic zones. And along the Mediterranean belt, you see that it's highly agricultural, and that's in the light tan. And along the sort of darker tan is the more industrialized countries of the UK, Germany, parts of France, Austria through there. And we see that there's a lot of energy use for the water and very little irrigation. And then as we go up north in the Nordic countries, very little irrigation as well. So again, we have this picture. There isn't one water use in Europe as well. And so the issues there tend to be where it's pollution, where point source pollution from our industries and our people. But with agriculture, one of the big issues is what we call non-point source runoff, which, and even regular rain-fed agriculture, is where we're putting fertilizer and pesticides on, and they're coming through the system. As well as a lot of work going on now, we're finding pharmaceuticals in our water systems because we're using so many of them that we take the water, we use it, we put it back in, but the treatment plants are not able to get these chemicals, and it's a very large issue out there. The other thing is we haven't heard much on environmental flows. Does anybody know what percentage of the Colorado River runs to the Gulf of California? 0. It's 0 is rounding down. It's some number like 0.00001 or something. All right, and that's legal. We don't have an environmental flow regulation here. So what was done is, this is the one piece of research I'll show you, is that work we did at the joint program is that for current world withdrawals, the middle term here is if we take environmental flows, and there are about 500 different measures of what is environmental flows, which is a whole area of science, is what is the water that the aquatic ecosystem needs. We don't know what it is, and it isn't necessarily the same amount every year. They want some dynamicism in it, like once every 7 years to be flooded, and those kind of things, which are really hard to model, so we ignore them. So, but if we look right now, if we put environmental constraints in that we know of, about 10% of the world's agricultural water would have to be removed. And if you know, in the Pacific Northwest, 250,000 acres of potatoes have gone out of production to protect salmon in the Columbia River. So what do we do if we want to have, there's a big push to have flow, 10% of the Colorado go to the Gulf of California. Who's going to lose it? Not Colorado, no. Arizona or California can, but not Colorado. So you see how it changes in different parts in North America. That's basically the Colorado. Really big impacts. So what is the amount? What does the ecosystem need to protect it? That's a really important issue. And we get into this nexus of water for people and water for nature. That's been a big debate going on recently. So how do we deal with that? How do we understand that is something that's really important. So what we have is we have these different demands. We have the water in one place and another, and then here along comes the famous engineers. And what they do is try to get the water to where the people are. And this is an example of the Colorado Big Thompson project, where the eastern slope of Colorado takes water from the state of Colorado, takes water from the western slope, the Colorado River, and through 4 tunnels that are through the Continental Divide, and brings it to the other side where there's now 2 million people living in the metro Denver area. And then that's basically a plumbing system with canals and pipes. And so, but we're not the first ones to do it. What's down there in the corner? Who are the first water movers? The Romans, with aqueducts. And many of them still are in use. So that was something. The next thing is, this is matching supply, demand, and time. This is the High Aswan Dam. We see here that this is the demand for water down the bottom for the winter and summer crops. This is how the Nile flow would have come, all in a flood. We store it behind here, and we're able to release it as we need it for the crops. And then you see the other reason for reservoir is this variability that we find in the Nile flow, which you've heard about maybe in the book of Genesis with Joseph and the Pharaoh's 7 years of plenty and 7 years of sorrow. There is a 7-year flow. The other thing that can happen is the geographic conflict of water. This is the Yellow River Basin, And all the irrigation is upstream in the Yellow River Basin. The demand for water in the cities is at the south. If we use the water for irrigation, there's none left. This is the 90 days of the year the Yellow River goes dry. So if the cities want that water to be there on the coast, they have to let it go and pass through the irrigation system and let it run to the sea. And so that's going to be an issue for how is China going to feed itself. Other really important issues, and the only person I want to point out in the room here is Susan Murcott, who has been doing amazing things related to providing water supply at the village level with appropriate technology, but others have been working on that in the work of Engineers Without Borders and others, is how do we get sanitation to the people? That's why we talk about economic scarcity. The water's in the streams in Africa, we just don't have the pipes to get it there and the cleaning to get it there. The other big issue is we're urbanizing. We're now over 50% urban. Urban water use is sometimes the order of 3 to 5 times more than rural water use. We then have to aggregate. We have pollution from that. That whole issue of urbanization is real important in dealing with these issues, and all of you are doing work on that. Finally, to focus on ecosystem health. We're seeing the biodiversity decreasing, and particularly in the ecosystems that are related to aquatic habitats, as well as the pollution on there. So all the work going on in biological sciences, in things related to the correction of pollutions with chemical engineering, how can we avoid this by treating our waste better and doing some of these other things in a better way. So finally, we come to the issue of there is a whole host of scientific questions. There are a whole host of engineering questions. How much can desalination provide us? How much can renewables help us? There are a number of projects going on campus. But the main thing we end up coming back down to is, what are the institutions and what are the economics telling us what we need to do? And how do we manage it? We know how to solve the Nile River water. We've been working for 11 years on the Nile Basin Initiative, getting everyone to speak on it. An MIT grad from the Parsons Lab across the street was the Minister of Water in Egypt until the Arab Spring. Working with the Ethiopians, we knew what to do. The Egyptians have failed to sign the new treaty on the Nile. We know how to build the dams. So instead we have conflict because the Ethiopians got funding from the Chinese and the Italians to build the Renaissance Dam, as well as taxing all their citizens. And they're going to dam the Blue Nile, which won't be a problem once it's full. But if they fill it, it's 50% of the flow entering Egypt. How do you come up with a way to fill it in an equitable way that doesn't hurt Egypt, but allows Ethiopia, who supplies 75% of the Nile, to use some of that? So how do we bring these things together? How do we do that? That's the issue. And so all the problems cross the disciplines. That's why I was so excited last year at Water Night. Every discipline's seeing how they're doing it. And what we do is, I think MIT is a place for this, that we can be if we want to get poetic, a beacon around the globe, because we work together. One of the things that I've heard from many people is, what is it about MIT is people can come together as teams and get things done. And that's a hallmark here versus some other universities where it's individualism. So I think the start of the Water Summit, the Water Team, this is what we can do. We get the initiatives there to cross those boundaries like Ron Prinn and Jake Jacoby did for the joint program, and to work in that area. And we have a perfect segue now to Professor Fisher, who's going to talk about the water problems of the Middle East. We've got lots of issues there related to cultures and animosities and history and war, and no water. Very dry. And economies and inequities. How do you develop and grow that? He's going to provide for us a story about that. So thank you for your time, and I'll be back at the discussion time for any questions. Thanks.